Okay. Can you guys hear me? There's going to be a bit of a delay because this is remote. So I'm going to give a handwritten talk. There's some prompts. Maybe I'll introduce myself. My name is Ryan. I'm a professor of computer science at ETH Zurich. And my lab is called Ricolab, which is like one of the famous Swiss products, Ricola. And it used to look more like Ricola's logo until we got a cease and desist notice. So now it's just the same font, which cannot be copyrighted. Okay, so why did I make this talk? So one day I woke up and I found that Sasha Rush had written a little tweet about my course notes. And I thought that was weird because I didn't really think anyone other than the students read my course notes, but there he was. And he said, well, this is really great, all this nice notation. And, you know, this was very flattering. I was very excited. I thought, wow, maybe I should talk to people about this. So here I'm going to give a bit about what I teach the graduate students in my large language model class. To start, so this is the third iteration of this talk I've given. So we're going to start with a bit more audience engagement because previous versions of this talk have had some reneging. So the first one is we're going to meet an AGI, and it's going to look like that. So I guess it doesn't look very friendly. But anyway, we're going to ask a question of this AGI. So I'm going to poll the audience. And the question is this: what formal computations do you think this AGI can do, this monster out there? So I'm gonna write some down, and I'm going to have you guys raise your hands. And you're going to raise your hand high if you think, yes, the AGI can do this computation. And you're not going to raise your hand if you don't. So the first computation is going to be, can it reverse a string? So do you think this Terminator situation, can it reverse a string? Oh, wow. Okay. We'll do another one. How about this? Can it execute a Python program? Anyone? Oh, fewer people. So you don't think the AGI can execute a Python program? That's quite interesting. How about this? Can it decide whether an English sentence is grammatical? And there's sort of like an ing sentence is grammatical. Anyone? Okay, you think it could do that? Now you can, of course, you can be a bit trollier about this question. Say, does that even exist? But anyway, that's sort of like. So I'm going to hold you to this. So I think, unless I didn't, maybe I was looking down for this one. But most of you think 1 and 3 are things this AGI can do. Okay, so now we're going to ask a question, which I drew here, and I'm going to put a little heart here, which is my interaction for this slide, which is why can't an LM be Chomskyan? And the reason I care about this is because I feel like, and maybe at lunch, Roger inspired me to be a bit more polemical. There's people who are creating a false dichotomy between formal linguistics and large language models, and it's really not getting at the heart of the issue. So I'm going to put a little caveat here about what Chomskyan means, because that's a wide spectrum of stuff. So I'm specifically going to focus on is some OG Chomsky syntactic structures, 1957. So we're not going to do with the stuff that came later. But that's what I mean by this. So in case someone raises their hand and said, well, what about the innateness hypothesis? That's not what I mean. Okay, so what we're going to get into now is I'm going to get a bit of an introduction about theory of computation. And I'm going to put down some definitions. And then in line with the theme of this talk, I'm going to go into how this sprung out of linguistic theory. And then we're going to tie it back to large language models. What is theory of computation all about? So I sort of have an interesting background. I majored in linguistics more or less, so it was cognitive science at Johns Hopkins in the end. And then I ended up as a computer scientist somehow. And I think these two fields are rarely brought together, despite the fact that they share an origin. So the most important definition of sort of theory of computation is an alphabet, and it's often called sigma, is a finite non-empty set. And an example of an alphabet, we get some very simple examples. It's not very hard. Maybe you've seen this in sort of a basic CS 101 class, would be this, it's a set of symbols. I have A, I have B. It's definitely finite. There's 2 of them, and it's not empty. Okay, so beyond that, the other thing that we typically talk about in theory of computation is we talk about the Kleene closure. And this is something I don't think I've ever seen in a linguistics course. So the Kleene closure of a set of an alphabet, is denoted with this little star, and it's going to be this sort of infinite union. And this is all the strings of length n, where the string of length 0 is defined to be the empty string. So this is sort of all possible strings. And I think that's sort of interesting because this is very obvious if you're sort of a mathematician, but less so if you're a computer scientist, is that this is an infinite set that's composed exclusively of finite things. And that fact's going to come back later in a big way. Just so we know, so this is an infinite set of finite things. And then we have what a language is. A language is a subset of sigma star. So this is a formal definition of a language. Now, with these three definitions, really this last one, I'm going to tell you everything you need to know about theory of computation at a high level. So theory of computation is about finding devices that say whether or not a string is in a language. So, I'm going to have some language and I want to decide. So the goal is to decide. So to decide whether a string is in a language. And there's a lot of sort of famous devices about this. There's finite state automata, context-free grammars, Turing machines, etc. And what's interesting about this is really, Chomsky's doing. He invented context-free grammars, and we have a lot of terms in computer science named after Chomsky, like the Chomsky hierarchy. And what's important for this is when I say Chomsky, I'm going to tell you the three things I take from him, and then we're going to switch over to LLMs. So the first thing I take from Chomsky, which, and I'm surprised that, for seeming political reasons, more people don't give him credit. The first thing I take from Chomsky is that language is a natural object. So in this sense, it's something that's worthy of study, like any other natural phenomena, and therefore the study of language is a natural science. And the second bit, which I think is really important, is that it should be formal. So we can formalize the study of language. And there's a lot more to say here, but those are sort of the 2 bullet points. So it's about half the talk. So now we're going to get right into language models. So the question now is, what is a language model? And this is going to matter in a big way. Because a lot of people are interested in proving formal properties of language models. They're interested in saying what a language model can or cannot do. But if you ever wanted to prove a theorem about a mathematical object, you'd have to start with a definition. So the definition of what a language model is, and this is sort of a historically correct definition, is a language model is a probability distribution over sigma star for some alphabet. Now, if you think about this, this is a complete generalization of what we did with sort of formal language theory, because you can always recover a formal language by looking at the support. So if we say, let P be a language model, then the support, that it's all those strings with non-zero probability, is a language. So in this case, we've just defined our object. We have this form, we have this distribution over sigma star. And there's a couple of things I want to say about this. What I think is useful is that we've now isolated what makes a language model, independent of its size, different than traditional linguistics, which is probability. It's right here, it's probability. And that's fundamentally what we need to discuss more than anything else, more than distributed representations, because as we'll get to, maybe your large language model implements a probabilistic context-free grammar, in which case all you've done is take a symbolic system and implement it with a neural network. And all you've confused is sort of different levels, sort of Mars, different Mars levels. And I think this is often lost. So, right. So there's sort of 2 camps of probability, and then I'll sort of keep going. So the 2 camps And there's a lot more to say about this as well as almost everything. This is more of just a screed of hot takes. So I call them the realist camp and the pragmatist camp. So what I mean by this is that you could be a probability realist. And that you could say that probabilistic computation is sort of fundamental to the cognitive architecture. And you could take that stance. And that's different than being a pragmatist, where you say, well, a statistical model over sigma star allows us to actually estimate something useful from data. It's purely a utility. It's purely just an assumption by convenience because we want to learn from data. And then you made no claim about whether humans have some sort of probabilistic computation going on. Okay. So the next thing I want to do is I want to sort of get at a couple different definitions. And the definitions I want to get at is I hear a lot of people, and these are the things that really sort of bother me, where they say a language model is just the next word predictor. I don't really know what that means, because almost every model of computation can be framed as something that just does one action at a time. So I'm going to sort of give a sketch of this basic idea that any distribution over sigma star, every single one, can be factorized as a next word predictor. So that's sort of almost in a sense, a relatively vacuous claim. So one thing I'm going to make sort of an aside here is I'm going to talk a bit about prefix probabilities. So this is one of those things where I think more people would do well to understand, which is a prefix probability of a language model is defined as this, where so it's the sum of all the different strings that could come after X. And this is sort of important because this is really what relates general distributions over sigma star to autoregressive language models. Because we want to talk about autoregressive language models. And this sort of relates to my larger point of don't just say it's a next word predictor. That's just a factorization. So an autoregressive language model is one where you typically factor the probability of the string like this, where we say, okay, the probability in a string of our language model is the probability of I should write that a bit better, an end of sequence token given the string, and then the probability of every word given its next character. And the reason these two things relate is that this over here, this is nothing more than the ratio of two prefix probabilities. So there's a very simple relationship between any language model. I can take any language model P, compute a prefix probability, and convert it into an autoregressive language model. Okay, so one big claim I want to make, because about 5 minutes left, and this is, I'm going to put this in red ink, because there's a lot of sort of general confusion in the literature, and it's not that the publications are sort of wrong or incorrect. It's more that the high level message is really lost in details, and that is no language model is Turing complete. And this is a very obvious fact if you think about it. In fact, it follows completely by how I defined it. If I define a language model as a distribution over sigma star, and sigma star only contains finite length strings, so if I generate it with probability 1, I sample something to finite length, which means I always halt. There is no Turing complete language model. No language model as it is a general purpose reasoner. That's sort of a fact. Of course, you could say maybe by general purpose reasoner, I mean something other than a Turing machine, but then you'd have to start defining your terms. So this is sort of an interesting fact. However, what I want to do then, in about the remaining couple of minutes before we get to the larger implications, one more slide. So one other useful thing to think about is that I'm going to define sigma infinity as the set of all infinite strings or sequences. over an alphabet sigma. And this is useful because we then say a sequence model. And in the current version of my course notes, I'm very careful to distinguish a sequence model from a language model is a distribution over sigma star union sigma infinity. So why does this matter? A lot of the models we write down and a lot of the Turing completeness proofs that you see, including ones I've written, they fundamentally rely on the fact that the model might not halt. That's the only way you can possibly get a Turing machine. The thing might have to run forever, something that you've often been told in various classes. But that means it has to generate something outside of sigma star. And it's not very hard to find such a model, but it wouldn't traditionally be a language model. So an example of sort of, actually, I'll give one more definition for an example, then we'll get into some broader implications as we wrap up, is that a sequence model is tight if it is a language model. So this was a big deal in PCFG land for a while because there's a series of influential papers about whether or not a PCFG would leak probability mass to infinite trees. And this is one of the things I always found that a bit mysterious my first couple of years in grad school. But then I sort of realized it's really easy. It's really easy to sort of imagine such a model that does that. For instance, here's one. I'm going to have a model, and we're going to have a little finite state thing with EOS has weight 0. So therefore, I emit an A with probability 1 and an EOS with 0. So I go around this loop forever and ever and ever and ever. This is a non-tight language model. It places probability 0 on sigma star. And I can encode it. It's writing a few lines of Python, and it'll just run forever. Of course, finite state machines can be non-tight, even though they're not Turing complete. But anyway, another big takeaway here is that we need sort of to even talk about sequence models, because this becomes a much bigger set, because uncountably infinite. We know we need tools for measure theory. So this is sort of an interesting problem, because you get right in the middle of probability theory, specifically advanced probability theory, and you get theory of computation. Okay, so the last slide, a couple things I want to talk about. These are just some basic questions which we have answers to. So in 2023, we proved an interesting theorem, which says that all transformer sequence model, and the reason I call them transformer sequence models because they're defined autoregressively, are tight. I'll call this a theorem. So what does this mean? If you continue the chain of reasoning, it means that every big transformer, no matter how big it is, stops with probability 1, which means it can't emulate a Turing machine, which means it can't do general purpose reasoning. And moreover, depending on the assumptions you make, it's likely farther down the Chomsky hierarchy. So I think for me, sort of the biggest question, and especially the biggest sort of open question that relates to this workshop, is about how do we bridge this all, is that if you go back to when I set this up with Chomsky, he gave a series of arguments that language was context-free, and Stuart Schieber argued that it was mildly context-sensitive and all these things. But nevertheless, if you take for granted that not only are transformers not Turing complete, they're much farther down the Chomsky hierarchy, how is it that we have this very non-expressive model that's modeling so many things well? And I'll tell you what I've taken from it, which is that transformers are relatively good, and these large language models are relatively good at imitating aspects of human behavior. And that's not because they're particularly good or powerful models. It's because humans aren't very smart. And I think if more people sort of took that view, you might say, well, how are we in this bizarre situation where I have a non-Turing complete thing, a thing that cannot emulate all these things, like provably cannot emulate all these, desiderata of our AGI, being touted as sort of a huge reasoning power. And yeah, that's sort of where I want to leave it. I'll note there's a handful of caveats about chain of thought and some other things, but this was a condensed version.